Welcome to the Deep Dive Best Practices for Amazon Redshift session. I'm Harshita Patel, an Analytics Specialist Solution Architect at AWS. By the end of this session, you will gain insight into a quick refresher on Amazon Redshift architecture, the automated table optimization feature, and how by leveraging some of the simple concepts you can further optimize your workload. This is a 400 level session, so let's dive into it. Amazon Redshift is a columnar architecture. It stores data column by column. It is massively parallel processing, where you can scale an Amazon Redshift cluster from 2 to 128 compute nodes horizontally. It provides a number of analytical functions such as windowing, support for geometric data type for special functions, hyperlog sketch data type, where you can run approximate count distinct on large subset of data. Native support for JSON, where you can store and analyze using the super data type. This feature is currently in preview. Support for stored procedures, where you can write stored procedures using PL, PG, SQL language. Materialized view, as well as user-defined function, where we recently integrated with AWS Lambda, where you can write user-defined functions in any of the languages that Lambda supports, for example, C++, Java, Go. The use cases for user-defined functions in Lambda, where you can integrate with Protectgrity for data tokenization, as well as you can do data enrichment and integrate with other AWS services, for example, DynamoDB. You can now call machine learning models for prediction using SQL in Redshift by its integration with Amazon SageMaker Autopilot. This feature is also in preview. Redshift seamlessly integrates with S3 serving as your data lake, where you have the ability to run your analytical queries not only on the data in Amazon Redshift, but also combine that data with the data in your data lake, providing you a lake house architecture. All of this combined is what makes Amazon Redshift, and it is a fully managed service. You as an end user, you could be using a SQL client or any of the business intelligence products such as MicroStrategy or Tableau. When you connect to Redshift, you connect using a JDBC and ODBC driver to the leader node. Now we also support Data API to do asynchronous calls with Redshift, and you can use Data API on a command line interface or any of the languages which are supporting Boto3. The leader node serves as a query coordinator. It parses the query, compiles the query, and sends that compile code to the compute nodes. And based on your data distribution, each and every compute node is working in parallel. This is what makes Redshift MPP shared nothing architecture. The parallel integration of the compute node extends to Amazon S3. When you have your data on S3 and you're ingesting into Redshift using the copy command, each and every compute node is working in parallel. When you're unloading the data from Redshift onto S3 in any of the delimited formats or Parquet, each and every compute node is unloading in parallel. Amazon Redshift is a fully managed service. It takes backups, incremental backups, at every 8 hours or 5 GB of data change. These are asynchronous in nature, and they are pushed streamingly in parallel on Redshift Managed S3. The elastic layer of compute, which serves as serverless layer between the compute node and Amazon S3, is Redshift Spectrum. So by default, when you have a Redshift cluster, you have the ability to leverage Redshift Spectrum, which provides you the ability to query the data which is sitting in your data lake in any of the open formats: JSON, CSV, Avro, Parquet, or ORC. You can also combine the data which is in your data lake to the data in Redshift Local. And this architecture has evolved with the introduction of RE3 instance type with Redshift Managed Storage, which allows you separation of compute and storage. So you can scale and size your Redshift cluster based on your compute needs for your workload, and you only pay for the storage that you consume. Redshift Managed Storage comprises of local SSD cache and Redshift Managed S3. Based on your query pattern, the most frequently accessed blocks are cached locally, and the steering of the data is completely transparent to you. One node in RE3 instance family can scale, provides you storage quota of 128 terabyte. You can scale the cluster from 2 to 128 compute nodes, providing you 16 petabyte of compressed storage. When you extend your data warehouse to your data lake, S3, you can have the data size in exabyte. To take it a step further with the innovation, for RE3 instance family, Aqua will serve as a hardware caching layer sitting between the managed storage and the compute node. This will significantly enhance the read performance. For any customer using RE3, Aqua is going to come for a ride. To continue with the innovation with RE3, the feature data sharing, currently in preview, provides you read workload isolation. For example, you have your ETL cluster producing the data, then you can share it with different departments or different areas such as sales, marketing, data science, without having the need to unload the data from your main cluster, which is ETL, and ingest it into your end user or consuming clusters. So you do not require data movement, and you can share this data in a secured fashion, and it's consistent. You can also do bidirectional sharing of the data between the clusters. There are different instance family or node types within Redshift. RE3 instance, which has 3 different instances, the 4x large and the RE3 16x large. We have doubled the storage quota to 128 terabyte per compute node. RE3X Plus, which was recently announced, provides you storage quota of 32 terabyte per compute node. Dense compute, which is backed by SSD, and dense storage, which is backed by magnetic disk. And we have seen a number of customers upgrading their cluster from DC2 and as well as DS2 to RE3. What if all the best practices that we are going to talk about in this session and the recommendations that we are going to discuss are available to you based on your workload? This is what Redshift Advisor provides you. It's available in the console, it runs daily, observes your operational statistics with the lens of best practices, and provides you tailored recommendation ranging from how to optimize your data ingestion, alter statements with the optimized distribution key and sort key based on the observation for table optimization, and cost savings for cluster which are not utilized. So Advisor observes your operational statistics and gives you recommendation. To take this step further, Redshift now supports this feature, auto table optimization. You can choose to enable this at a table level, and when you choose to enable it, it automatically applies the distribution key and the sort key as observed based on your workload. You can also see what recommendations were made and get an audit trail of when those changes were applied using the system tables. Now let's dive into the concepts with Redshift. And when we dive into this concept, we want to look it through the lens of Redshift is MPP. When you run your workload, how you can optimize and leverage each and every compute node to work in parallel, as well as reduce the I/O, whether when you're running a query on a compute node or in between the I/O between the compute nodes. So let's dive into these concepts. So the first concept is compression. When you ingest the data from raw into Redshift, it provides you 3x to 4x compression. It serves 2 purposes. One is cost savings because now you have a reduced storage footprint. And secondly, query performance because it reduces the I/O. Redshift automatically provides compression when you're creating a new table or when you run a copy command for the first time onto an empty table. And now Redshift supports alter table statement to change the encoding of an existing column. You can also run analyze compression utility. Again, when analyze compression utility runs, it would give you the brute force recommendation on encoding, which is going to save on storage footprint, but might not be as performant. Let's take a look at this example where we are creating a table, deep dive, and we are defining 3 columns with a data type. Redshift automatically assigns the encoding of AZ64, which is the most performant encoding for numeric date timestamp. Each of the column can have different encoding, so they can grow and shrink differently. And for LZO, for varchar and character columns. The second concept is blocks. Redshift has very large blocks, 1 megabyte immutable blocks. It can store when you can have super compression close to millions of values. The concept of zone maps. So zone map is an in-memory metadata which stores minimum and maximum value of the blocks. The main purpose of zone maps when you run a query, it tells the optimizer which blocks has the data, so to prune out the blocks from the disk that does not contain data, reducing the I/O. Data sorting, again, helps to optimize the zone map. Data sorting is how your table is physically sorted on the disk. And when you define a table, you can define a sort key. And the sort keys, the main candidates are frequently accessed columns in your query, starting with low cardinality being the first column in your query. Let's put these concepts together of blocks, zone maps, and data sorting. We're going to run a very simple query, count distinct, filter by a date. So Redshift Optimizer, when this query is run, it prunes out the block that does not have the data, leveraging the zone maps. When the table is physically sorted, the zone maps are completely sequential for each of the block. And when this query runs, it's only going to access the block that has data, so significantly reducing the I/O and hence improving your query performance. Data distribution. The goal of data distribution is how you can leverage each and every compute node to work in parallel. From a joint performance perspective, have co-located joins. There are different distribution styles in Redshift. The first is distribution style key, a great candidate when you're joining two very large fact tables or tables on a column. That column becomes the distribution key. Redshift is going to take a hash value of that, do modulo, and distribute the data across the compute nodes and the slices. Distribution style all, where Redshift takes a copy and puts the copy of the table on each and every compute node. A great candidate for distribution style all is smaller tables like dimensional tables, less than 3 million records. Distribution style even is where Redshift is going to do a round robin and distribute the data across the compute nodes. And distribution style auto, where Redshift will automatically handle the distribution style for you based on the recommendation and your workload patterns. Materialized views are supported in Redshift, where you can leverage the materialized view to physicalize your very complex queries. With materialized view, you can join n number of tables, you can have aggregations, you can select subset of columns, as well as have filters. What this helps with physicalizing the complex query is helps improve the end user query performance, as well as it helps with your ETL. When your underlying base tables are changing incrementally, you can refresh materialized view incrementally. Redshift now also supports auto query rewrite and auto refresh for materialized views. With materialized view, you can have a different distribution as well as a different sort key, which can be different than your base tables. So to summarize all the concepts together, if you're embarking your journey on Redshift or you have a new workload, start with auto table optimization. Use materialized view to physicalize your complex queries. And if you choose to fine-tune it, apply compression on the columns. When you're working with the sort keys, start as the first column in the sort key with a low cardinality, for example, a date column. When you're distributing your data using the distribution style key, start with a high cardinality column, which will allow you to spread the data across the compute nodes. Data ingestion. The most optimal way to ingest the data into Redshift is using the copy command. In this example, we are using RA316X large, which has 16 slices per compute node. In this example, we only have one file, When you run the copy command, only one slice is doing the work. Versus when we split that file into 16, each and every slice is working in parallel, which significantly increases the copy performance. I would recommend to use simple delimiters with file sizes between 1 megabyte and 1 gigabyte after compression. An alternate way to ingest the data into Redshift is using Redshift Spectrum. Number of customers are using Amazon Redshift Spectrum for ELT. With Redshift Spectrum, it allows you to select subset of columns, push down the filter, apply transformation and aggregation before ingesting the data into a Redshift table. Redshift is more geared and tailored towards OLAP workload, not so much for online transactional processing for pinpointed inserts, deletes, or updates. When you do a delete in Redshift, it's a logical delete, and when you do an update in Redshift, it's a logical delete and an insert. With Vacuum, it serves two purposes. One is reclaiming the deleted space, and secondly, globally sorting the table. Redshift has support for auto vacuum delete, which runs in the background, as well as auto table sort, which based on your query patterns, it would identify those hot blocks and it would sort that data, which is a lightweight version of vacuum sort. If you have to run vacuum, you can run it during off hours and you can leverage this boost option, which significantly improves the vacuum performance, but also it's very resource intensive, so you can choose to run it during off hours. Auto-analyze, where it is analyzing the tables based on your pattern, prioritizing the tables, which needs to be analyzed first. It's running in the background, handles the work for you. But there could be some use cases, specifically in your ETL pipeline, that you might want to analyze the tables, specifically on the columns which are being filtered in your ETL pipeline. Workload management. When you have a data warehouse, you have mixed workload. You have ELT workload coexisting with your ad hoc, your dashboard, and data science workload. And in order to have this mixed workload coexist efficiently is what is the purpose of workload management, where it allows you to prioritize your most important workload and throttle down the low priority workload. The concepts within workload management, the first is short query acceleration. The way this feature works, when Redshift identifies queuing is occurring, it would, based on machine learning, it would identify these queries are going to complete in seconds. So instead of having your short queries wait behind the long running queries, it's going to start routing those queries to short query acceleration special queue. Feature concurrency scaling, it's a significant feature which allows you to automatically handle your spiky workload. So with concurrency scaling, when you choose to enable it, when Redshift detects queuing is occurring, it spins up transient cluster. It starts routing the queued up queries to the transient cluster, giving you additional horizontal scaling capacity equivalent to your main cluster size. When the depth of the queue goes down, it relinquishes this transient cluster. And all of this happens spinning up the cluster in a matter of seconds. And this is completely handled for you by Redshift. What you choose is enable the feature and specify how many transient clusters you want to use between 1 and 10 is a soft limit. With every 24-hour use of your main cluster, you get 1 hour of free capacity for concurrency scaling. Say your main cluster is up and running for 30 days in a month, you get total of 30 hours. And you can choose this free capacity at any given point of time in a month. Concurrency scaling allows you to handle your spiky workload for read-only queries. You can also apply cost controls with concurrency scaling now. QMR. A number of times customers ask the question, how do I protect my cluster from runaway queries or poorly written queries because they are resource intensive? With query monitoring rules, you can apply it at the grain of WLM. You can specify, hey, if a query is taking more than 30 seconds or 30 minutes for your dashboard queue, or the query is returning billions of records for your ad hoc query, or the queries, spectrum queries are scanning terabytes of data, you can apply those rules. And when a query meets those rules, you can take automated action. Log the query. So for the long-running queries, you can review what that query was and apply further optimization. You can abort or kill those queries, or you can deprioritize those queries. Automatic WLM. The main goal of automatic WLM is to simplify workload management, where Redshift automatically handles the number of concurrent queries as well as the resource allocation. Within automatic WLM, you can define different queues and say a queue for ETL, a queue for dashboard, and you can give query priority. Say you always want your dashboard queries to get the highest priority. And short query acceleration is automatically turned on. If your workload is predictable and you're using manual WLM, I would highly recommend you to enable short query acceleration. You can have a queue for data ingestion where you're specifying 2 concurrent queries, providing memory of 20%. So each of the queries is going to get 10% of the memory. Having a dashboard queue with higher concurrency, turning on concurrency scaling to auto, and a catch-all default queue for ad hoc queries which are data intensive, having a concurrency of 3, providing it a memory of 30, so each query will get 10% of the memory. There is also a hidden queue, which is a super user queue, and I would recommend to use super user queue for administrative purposes only. To summarize all the best practices, if you're starting your journey on Redshift, or if you're using the old manual WLM, switch to automatic WLM. Implement query monitoring rules to protect your cluster from runaway queries. And if your workload is predictive, you can implement manual WLM, and the recommendation would be have fewer queues, 3 or 4 queues. And the concurrency, the number of queries across those queues, set it to 15 or less, having in mind that it's more about query throughput for your workload. Cluster resize. So a number of times customer asks, I want to right size my Redshift cluster, as well as I want to resize my cluster or change the instance type of my cluster from DS2 to RE3. So with cluster resize, Redshift provides you a widget when you're creating a cluster where you can specify what is the volume of your data, what is your frequency pattern, and it will give you a recommendation on the cluster size. Within Redshift, there is classic resize and elastic resize, which we'll dive into a couple of slides. If you have a snapshot, you can take, say for example, you have a snapshot for DS2 8x large and you want to resize it or restore that snapshot to RE3, you have the ability to do cross-instant restore from a snapshot to a different instance family, as well as change the number of nodes. Let's dive into classic resize. In this example, we are starting off with RE3 16x large, 3 compute node. So the total number of slices is 48. When you instantiate a resize with classic resize, Redshift provisions a new cluster. It adds with a cluster of 4 compute nodes. It puts the main cluster into read-only, does the binary transfer of the data, and when the binary transfer of the data is completed, it switches the DNS. So we started off with a 3 compute node RE3, we end up with a 4 compute RE3 with total of 64 slices. And with classic resize, Redshift will distribute the data across the compute nodes and slices. Elastic resize. Exactly the same example, RE3 16x large, we are starting with 3 compute nodes and we want to resize by adding 1 more compute node. With elastic resize, Redshift adds a new compute node to the existing cluster. It takes an incremental snapshot, pushes to S3, and there is a duration of 4 or less than 4 minutes where Redshift moves the metadata or the slices. During this duration, any new queries that you're submitting will be parked. If there is a write query within a transaction, it will roll back. And Redshift will finally start hydrating the data on the new node from the snapshot taken on S3, starting with the hot blocks first. During this duration, your cluster is available for read and write. You can also schedule elastic resizes. So when to choose elastic resize versus classic resize? The common use case for elastic resize is when you have a known window where you require additional compute capacity. Say, for example, Monday morning, or a quarterly refresh, or a weekend refresh, where you have the given SLA complete your workload, but you're churning more volume of data and more complexity of the workload, but still within that SLA. You can resize up your cluster before the workload starts, and with Redshift, it provides linear scalability when you have more compute node. You complete your workload, and when it's completed, you can resize down the cluster. With classic resize, if you have an existing cluster and you want to encrypt that cluster, behind the scenes, Redshift uses classic resize. With both elastic resize and classic resize, you can change the instance type, you can change the number of nodes. And with elastic resize, for example, if you have RE34XL or RE316XL, with elastic resize, it allows you to go 2x the size or 1/3 the size of that cluster and every incremental point in between. When any of the scenarios fall outside those boundaries, you can choose to use classic resize. And the basic distinction between the two resizes is the amount of time it takes. With elastic resize, it's less than or equal to 4 minutes during which the queries are parked, and classic resize, the time it takes, is a factor of the amount of data in your main cluster. I would love to leave you with additional resources on top 10 tuning techniques with Amazon Redshift, best practices on Redshift Spectrum. If you are a new user to Amazon Redshift or embarking your journey on Amazon Redshift, we would love to engage with you. Please reach out to your account team. And thank you so much for your time. Take care.